Hey, y'all. Welcome. It's good to see y'all. Thanks for hanging out at the end of the day. It is nice to see your faces. I'm James.
I'm Deepak.
And we are here today to tell you a little bit about our journey to Kubernetes, the potholes we hit along the way, and some that we swerved to avoid. I'll give you a quick bit of background, kind of where we started from, how we started on our journey. Deepak's going to walk you through the tools we had on hand and how we deployed them to solve some of the challenges we had. And we'll close with a demo that you can kind of take home, kick the tires on, twiddle some knobs, get a feel for the sorts of configurations we're talking about here today. A little bit of background. We work at Procore. Procore aims to build the software that builds the world. Our customers range from small subs to enterprise GCs, building buildings a lot like this one. We work primarily on Cornerstone, which is our legacy Rails application from the dawn of time. It predates GitHub, so literally is prehistorical as far as I'm concerned. These days we have a large kind of constellation of microservices around it, but like Cornerstone is still a kind of core to the product. We have like 90-ish teams working in the ecosystem, and our contract to them is that we will deploy as continuously as we reasonably can, given the scale of that artifact and kind of complexities there, which works out to about 9 deploys a day. It's an interestingly heterogeneous workload. We've got weird, wonky reporting queries that take 2 minutes served out of the production database for reasons best described as legacy software. It is a legacy system, and I say that with love. I love software that has a legacy, I think I'm paraphrasing a quote here, but for you to get this story, it's important for you to understand some of the specific ways that our monolith wasn't happy. If you have a legacy system, yours is probably different, and there's no substitute for spending some time thinking about that, but we're going to tell you about ours. Before we got started working, we were running on auto-scaling groups, and I say auto-scaling extremely loosely here. The only scaling we did was at deploy time. When we had a new code version, we would spin up new nodes with new code version. We would wait for 80% to be ready. We would hard cut traffic, keep the offside warm for a time, let those requests strain, generally wait for the next deploy to kick off and repeat. And if you're thinking to yourself, man, that sounds really wasteful, you're in good company. Those were some things we wanted to change. I think if you dig a little bit deeper, a lot of our problems stemmed from it was hard to change things. We were running on kind of bespoke scripts that had become load-bearing. They were difficult to reason about. They were difficult to change. We were afraid to do so. So we had just a lot of legacy debt that stacked up behind that, right? If you're thinking to yourself, M5 sounds pretty old, what are we talking about here? Like, again, yeah. So I think Deepak and I are on the team somewhat recently formed whose job is to keep this like heart of the business from sclerosing. So when we sat down and looked at opportunities, this felt like a good one. It felt like moving this onto a solid foundation of Kubernetes could be a real win for us. Here's a little bit of what that calculus looked like for us at the time. We knew there would be challenges, right? Like this application predates the concept of cloud nativeness at all, so it's not going to be a natural fit like you'd want. In particular, the long startup and shutdown sequences were going to pressure test us a bit. But we had some things going in our favor. If you kind of squint at the architecture diagram, you can see something that sort of looks like a pod, right? We've got a primary container, we're containerized already. We've got some sidecars running next to it. In particular, we're already routing traffic through like an Envoy sidecar. So we had a relatively obvious kind of next target state in Kubernetes. It's not where we want to end up, but you can imagine a deployment running Kubernetes kind of prove out that transition point and keep one moving piece out of the equation. A few other things. I wish there was more time to talk about the like popping the hood and working in the application, right? Like slow startups is a problem you should work from both ends. It's just the application side that work across all of our 90 dev teams is very different characters. That's a talk for a different con. The other thing I really super want to emphasize here is executive support. Like we had the good fortune to have air cover for doing some foundational rework without immediate kind of payback. That's not a given. It's also never going to be a blank check. I think you have to be aware of like when are your executives going to get cold feet. For us, we knew like we couldn't cause high profile outages. We couldn't get stuck in the same way our old system was. So this was kind of the needle we had to thread. We zeroed in on this as our key hypothesis, right? We need to prove with receipts in production that we could tighten up our scaling behavior without anyone noticing. So this means not impacting our deploy cadence for our developers, not serving 503s, not causing any incidents along the way. And we set to work on this, right? Like we kind of deferred any of the cleanups we wanted to do that weren't specifically here. We tried to spend all of our innovation tokens proving this out with receipts and prod. Here's the timeline. We felt like we had about 6 months to get this going in production, so we spent the better part of the first 5 kind of going 0 to 1, getting the foundational ducks in a row, making sure we could do this safely and iterate at a reasonable clip from there. Deepak's going to tell you a little bit more about what that looked like in practice, walking through that path.
Thanks, James. So as James was mentioning, the hypothesis is that when we migrate to Kubernetes, we can tighten our scaling behavior without our internal customers or external customers knowing about it. But the reality check is we all have weaknesses in terms of migrating this project. We know the weaknesses. We have opportunities that we have to explore. And then we also have threats in terms of a failure and the risk around this. So to address all of that, we spent decent enough of time, but not too much time again. We had to show progress in delivery as well to set some design principles for building crafting the foundations of this platform. So the principles are the components that we're going to use to build this platform has to be CNCF or an open source within a K8 ecosystem. There's nothing that we have to think about tailor-made solutions for this to maintain and manage this platform. We need to have agility to move fast with the confidence. That's the principle. We also need a flexibility, as you can see here, a flexibility to avoid drift. As you can see here, the global defaults on the screen is a basic layer that gets to all the clusters, but we want to experiment something with a specific component upgrades or specific type of changes around any controllers. We have a flexibility in terms of making those changes and try them in the lower environments before we try them on production. And the main two core principles, if I have to talk about, is it has to be a GitOps fashion. We use Terraform for a bare minimum to get the control plane up and running, for getting all the required secrets and ISA, which is IAM service accounts to be created, all the basic minimum AWS services that are needed for our Carpenter SQS and all of that. So that's a part we use Terraform. Rest is all about what we use GitOps. And the second core principle is that we need a declarative tagging that is consistent across all our resources in the cluster, across all regions, so that pays a dividends for us in terms of observability, service cataloging, auditing, and cost centering. As I said, we use GitOps. So Argo CD is our deploy tool for as soon as the control plane is up with Terraform, as soon as the cluster is with Argo CD, all the bootstrapping of controllers and CRDs happen through Argo CD, and application still gets deployed to our homegrown solution, which triggers a deploy through Argo CD. As you can see here, the overrides in terms of the values files, we use Helm heavily, so we have overrides at different layers. These are our operators and controllers that we use. Specifically, if I have to talk about the Ingress controllers here, Ingress, and we recently migrated from an Ingress to a Gateway API to have more control on the layer 7 routing at the platform layer. We'll talk more about it when we saw topology in the next slides. So we are in Kubernetes conference. So let's talk about basic Kubernetes object and resources and components as a one-on-one topic that will help for the next few slides. So Kubernetes has pods. That's a basic minimum deployable unit of compute that you can deploy and manage in Kubernetes. There are services which expose pods to the external world. There are these Ingress gateway controllers. Every object and resource depends on the endpoint slice object, which has a state of your endpoints in terms of whether they are ready to take traffic or they're serving traffic. What's the state of current running pod? Is it in termination state or not in termination state? So that being said, our first gotcha when we started experimenting things, we have learned that there are some primitives in Kubernetes that would help us to balance between the deploy time and we have to de-risk our developer velocity in terms of deploying changes, right? So that's a deploy time. We don't want to increase the deploy time, so we risk our developer velocity. And we have to balance the cost of infrastructure and operating it. And we also have to balance the application availability. And the primitives that we have learned as of this is the max search and max unavailable, the deploy spec, and our rollout strategy attributes. And the main important thing is the Carpenter batch ideal duration. Our goal is to ensure that we don't spin up new nodes when we are trying to deploy. Our goal is to ensure that whatever the pods we are terminating, we can place the new pods on the same node in the place of the old pods. So that's our goal. And that's what the batch ideal duration defines. And we have to make sure our pods are terminated within the duration period So a carpenter doesn't decide to create a new nodes and then consolidate later, which is a penalty in terms of consolidation. So we want to avoid it. So these are things that we learn. And the termination grace period is something that is new for us. And we want to make sure the parts are not terminated before we run any pre-stops or anything. So we have set a termination grace period to be max request timeout in our application. And the second gotcha is of the help probes. So the way we use help probes, and if you have to take a few things from this slide or from this gotcha, is that the startup probes, we don't set any initial delays seconds. The reason behind that is we keep on optimizing our boot time of our app, and we don't want to come and change any of these settings across our clusters or across the deployments. And then the failure threshold has to be 2x of your boot time, average boot time. That means that your startup probes will not fail. They will succeed at some point. So if you ensure that these settings are properly configured, you'll have a healthy app in a rolling deploy that will start serving traffic based off your startup time of your app. And one thing I want to call out is the liveness. So liveness, make sure your period of seconds for liveness is always the entire failure threshold of your readiness checks. And don't make your liveness to be more frequent than your readiness checks. Those are things that we learn as an experimenting it and making sure, because we have a slow start of an app and a shutdown of an app. So we just tuned it in a way that it makes it creates the app and passes the health checks as soon as it can. And the container lifecycle hooks is something that we have leveraged to ensure that we gracefully terminate connections before shutting down the pods. We will get to see that in the demo in terms of how we did it. The sleepx doesn't work in our case because of the app size. The app size, a pod is of a size of 12 cores CPU and a 30 gigs of memory. So we have the simple sleepx doesn't work because of the app behavior. And then post starts is something we undo the actions that we have taken in the pre-stop cycle. The reason behind that is if something goes wrong with the liveness or if the app container restarts, the sidecar that is sitting as an envoy, any actions that we have triggered to envoy during the pre-stop cycle, we have to undo that so that when the app container restarts, envoy is ready to take traffic and serve the traffic to us. And we have gone through 3 iterations of these lifecycle hooks. We started predated before native sidecar is a thing in Kubernetes, that is before version 1.28. And 1.29, I believe the native sidecar has become stable. But this is all before 1.26 is when we started, and we don't have a way to synchronously, we don't have a way to orchestrate the shutdown sequences between Envoy, the PG bouncer, all of the other sidecar containers, because as you get a as the pod goes into termination cycle, all the sidecar containers will get the SIG term at the same time. But we cannot pay the penalty of losing connection that is in flight right now. So we have gone through 3 iterations of pre-stop cycles. We're going to show you what those are. And today, as of today, on the right side, what you see is the current state. We only run one pre-stop from the app container that will tell Envoy to gracefully terminate the connections. As you can see in the first iteration, I'm not sure if it's visible, but we have a shutdown container that would, it's everything depends on MTDAR, and there is a state file that is written by the shutdown container, and that state file is monitored by the Envoy and the app container, and if the file exists, that's when we say the pre-stop is successful for the app and Envoy containers. And the second iteration I was mentioning to you, when we moved to native sidecar, we completely removed the dependencies on MTDIR on the custom sidecar container. We just removed it. And then we switched from a /drain listeners to the health check fail. The reason, again, this is the learning for us. The drain listeners will drain all the listeners of the Envoy. And in case if app container restarts, there's no way you can undo that action of drain listeners. You have to restart the entire pod. But the health check fail will only fail the health checks of the Envoy. And there's a reverse mechanism where you can say health check OK to undo that action so that the Envoy will become ready to serve traffic when the app container is up and running. And then when the iteration 3 is that we migrated recently, as I said, a month and a half ago, to Envoy Gateway using Gateway API. We were using ingress API, controllers before, but when we were on AWS LBC controller, it was taking around 30 seconds, a minimum of 30 seconds for its endpoints to be updated on the target groups. With Envoy Gateway, what we have seen is the control plane removes the endpoints that are not serving, that are not in a serving state within less than 3 seconds. So we have to iterate our pre-stop as well because we don't want to keep our containers sitting there if the data plane doesn't have information about a terminating container. So let's see that in action. So as I was telling to you, we have gone through 3 iterations. So this, like I said, SleepX doesn't work for us. So there's a base manifest. There's a base manifest, as you can see here, which is just saying SleepX for X number of minutes in X number of seconds. You can increase that to 60 seconds, 5 minutes, but you're still holding the pod. Even though you don't have connections, you're sleeping, literally sleeping, and you're just wasting resources where you can't fit the new pods in the old pod space. So since this base, for sake of time, I have deployed this base manifest already. You can see I have 10 replicas running currently for that workload. And what I'm going to do is I'm going to deploy the refined version. I'm going to deploy the refined version of pre-stop hook. And you can see the pods will go, we can see the rollout deployment is happening right now. And you can see the metrics coming in, and you can see the active rollout is happening right now. Where I said 20% is the max unavailable. As you can see on the old replica set, we lost 2 pods. And then the new replica set is trying to bring up the new pods right now. As this is happening, you can see the old container right now. I have 4 screens here. One is showing the pod view. The second, this screen is showing you in terms of what's happening at the pre-stop state of a container, of a pod. And then if you can see here, this is showing you any logs coming in from the Envoy. And this is the live traffic that's going in. So we'll come back to it as the deployment takes some time. It has to circle all the old pods to new pods. It'll take some time to get the new version up and running. In the meantime, let's go and talk about the new gotchas that we have learned with respect to the HPA. We haven't done an app like this in terms of dynamic scaling. In the back in the space of ASG, we have done like schedule-based scaling, like cron-based scaling. So that's a new avenue that we have to explore. That's an opportunity for us to learn what we can learn from dynamically scaling a scale of this app. So we use K8s for that. And K8s has a pooling interval, which is flexible. But Kubernetes has the HPA object as autoscale sync period. That is not tunable in EKS space. Or if you go to any cloud providers, what we have noticed is that that particular setting is not tunable. And from our observations and insights, what we have noticed is that by default, it's set to 30 seconds on EKS. And it only matters when you're going from 1 to n. If you're going from 0 to n in terms of a scale, then pooling interval matters. But if you increase the pooling interval to 60 seconds, but the sync period is the one which takes the priority from going from 1 to n. So the true minimum reaction time that you have is whatever the sync period that is set by the cloud provider. Unfortunately, we cannot tune it. But you need to ensure there's the built-in stability mechanism within HPA, which is the plus or minus of 10% tolerance for both scaling in and scaling out. This prevents the flapping behavior, which we have spent, that is kind of tunable right now with 1.33 version of alpha, which we want to experiment. That plus or minus 10% is the tunable, the tolerance is what we have to play with in terms of a scaling down strategy of the behavior of the app and everything. The scale up, we don't have any set behaviors. We want to scale up as aggressive as we can. In scaling down, at the same time, we don't want to scale down n number of pods by losing the capacity so that will end up serving errors to the customers. So in terms of behavior, you just have to do an experiment of yourself. adjust the policies based off your traffic pattern changes. When I say traffic pattern changes, let's say our traffic patterns in terms of peak hours ends around like 2 o'clock Pacific, but sometimes that traffic pattern changes. So we have to keep observing and get the signals out and keep adjusting the scale down behavior so that you don't impact customers. And always have a fallback. When you're using KDA, make sure you have fallback. If you don't set fallback and your metrics providers have issues, like in our case, Datadog, nothing happens. You will be at the scale of whatever the scale that you are running in terms of replicas when you lost connection to your metrics provider. But what we have said is our fallback is 80% of our max replicas so that we always have 80% of capacity to serve traffic because our tolerance of max unavailable is 20%. So we can lose 20% of capacity, but we can still serve the 100% traffic on 80% of capacity. And we use Argo rollouts today. So we were doing like progressive, like rolling updates before using deploy objects. And then we moved to Argo rollout to have a canary. And canary is another area of opportunity for us to prove that this size of an app can be done on a canary rollout because that will give us an assurance that we have analysis templates that are set to ensure that a new version of app doesn't have any bugs that are not highlighted during the testing phase. But we send live traffic to the canary. We observe the analysis. We do analysis on the observations, making sure that we're not serving errors. It's a ratio-based analysis between stable versus canary. And then we make sure that we continue to set weights, increase the set weights in terms of rollouts. And then in this case, the max available budget isn't valid. Even if you set a weight of 25, 35, but your max available is 20%, it is still, the rollout will still be at 20%. So I want to call out, and again, the rollout is it's not a batch operation. It's a sequential operation. As you lose the parts on the stable replica set, the new part gets provision on the canary replica set. And max surge is a trade-off between deploy time and cost. So if you want to get your deploy time faster, you can increase your max surge. But your max unavailable is lower, you still have to wait. So that being said, before we go and talk about this gotcha, let's go back and see the observations. As you can see, when we did on the SleepX, and we were trying to shut down the pods, you can see there was errors in terms of 503s served to the customers, and these are upstream disconnects. It means that the app container has been terminated before Envoy could get a response. So as we rolled out the updated pre-stop hook, which is not a static SleepX, what we do is we go and command Envoy to fail his health check. So that way, what happens is at that point, Envoy will send a connection close request to the clients. And then we keep checking the total connections within the Envoy metrics to ensure we have 0 connections. And then we keep watching for those connections to be 0 for 3 consecutive attempts before we say a pre-stop is success. To see this in action, let's go and make a deploy. Let's do something like that. And let's do a deployment. I just deployed this version, so let's do this. Okay, so now, as you can see, again, a deploy is rolling out. We'll come back, and as you can see here on the screen already, as a pod receives the termination signal, as you can see, we are keeping a track of active connections in Envoy, and then when all the connections are gracefully terminated, that's when we would go and send a successful pre-stop being a successful. And now the SIG gets to the app container, and then app gets the pod gets deleted. And as you can also see, that particular pod hasn't served any errors right now. But again, don't take my word. Just keep watching as the deploy rolls out. What we have seen before is we have seen a bunch of 503s being served to the customers. I can also just stop this and then just concentrate on 503s. As you can see, the first container, the first pod has been terminated, and we'll come back to this to see if it works. And can we eliminate 503s completely? Yes, it is a trade-off level of efforts to optimize app versus cost involving in over-provisioning your clusters. So there are four layers that influence this. The size of your app, the image size of your app, the application boot time, obviously, and the traffic distribution and splitting your workloads at the layer 7 routing. What I mean by that is if you're running the heterogeneous, like as James was mentioning, we have a number of heterogeneous workloads served from the same pool of web pool. In this case, a traffic distribution of splitting means you're going to split that into type of workload. You're going to split the web pool into different web pools. Using layer 7 routing, you can route them to a specific web pool so that now you can define the scale behaviors for each of those web pools based on the traffic being received. And the cluster auto scaling and application auto scaling. These are very much important. As I said, if you're ready to put cost, you can over provision, have enough capacity to serve the traffic. In our case, it's not the case. So the old topology, we were actually, the blue that you see is owned by a different team, which is traffic platform team. The yellow boxes that you see is owned by us as a Cornerstone platform team. So previously, when the request comes in and we are about to scale, we have buffer in terms of capacity, but as I said, sometimes the traffic patterns can be dynamic and we get a surge of traffic, but our scaling mechanics hasn't created enough workload, enough pods to serve the traffic. At that point, some of the requests can fail to connect, not like close, in the sense that they cannot connect to the app because we don't have enough workers to serve the traffic. At that point, that traffic doesn't leave our infrastructure. It will go and do a transient retry from a routing service so that now when that routing service will again load balance, it will send the traffic. Now the load balancer based on a least connection algorithm will send to the pod that has enough workers. That was the old topology. It was going to a traffic platform team routing service. In the current topology, since I was telling you, we moved from an ingress to Envoy gateway, we created our own data plane. And now all of our retry logic that I was showing you will happen within our data plane that is owned by us. And we have been iterating on top of it in terms of pushing changes, experimenting it, and iterating it. And the future topology is this. As I was telling you, we have different workloads, heterogeneous workloads served from the same web pool. And now that single web pool serves all different traffic. And we also might be sometimes over provisioning for certain workloads. So that's the reason if you split the workload like reporting, integration, strategic customers, we can dynamically decide in terms of what scale we have to assign for each of these workloads. And again, all of those are funneled through a data plane that we control. So we can fastly iterate and we can ensure that the reliability of the platform for our customers. So let's go back and see the observations here. As you can see, every pod that is going through a termination period and the pre-stop is ensuring that all the connections, you see like when the pre-stop started, it has active 13 connections and it started slowly observing in terms of how many connections left to be closed or drained. And finally, it has closed all the connections and it has been cross-checking to ensure that, I mean, we want to make sure we are not getting any in-flight, any new connections to the pod. And then if you're not getting new connections, then we exit the pre-stop handler. At that point, the term signal is sent to the container, because the app container. At that point, that's when the pod gets terminated. And as you can see, this is a zero downtime. We haven't served any errors like what we had with the static sleepx. All the pods have been recycled without showing any errors to the customers. There was one that was specific to probably not available resources. Again, that would be retried from our, that will be tried from our internal routing service. In this case, I don't have a routing service, but the data plane that I was talking to you, those kind of requests will be served or tried from internal data plane. Lastly, I want to call out kudos to our two top engineers who has contributed around 17 PRs for the open source projects like KDA, Argo rollouts, Argo CD, and out of 17, 50 were met successfully. So this is all from our learnings in terms of building this platform. We have found that there are some things that doesn't work or doesn't fit to the use case of an app at this scale, and we have contributed back in terms of our learnings, and they have been merged, and we have been using those features now. And key takeaways, again, you definitely need executive leadership buy-in on your plans and your approaches. Definitely you need a commitment from the leadership on this. And second thing is observability first. Do not ever think observability will be something that you can create later, you can add it later, because without any signals to watch, there's no way for you can iterate faster and then make it better. Test success and failures in your lower life cycles. Set up some playground environments, developer environments, keep trying until you succeed. Think about unknowns from your app perspective. And then that's where you spend most of your innovation tokens in terms of ensuring that you test and fail and learn. And optimize for quick iterations. And again, this is where you would set up your PRs, having a mechanical diff that is added as a comment in your PR reviews so that you exactly know what kind of changes are going when you measure this PR and what kind of, and where exactly it's going, in which cluster it's going. So that's where we have spent time as well to make sure we have the confidence when we review a PR, we can measure it immediately. And today, as of today, the rollout time is we have 3 clusters across 3 different regions. Sorry, we have total 15 clusters for Cornerstone platform across 3 different regions, and we roll out to all clusters within less than 10 minutes, and the rollback is the same pace. Lastly, thanks for all my colleagues at Procore who made this possible, and thanks for all you guys for joining at the end of your day. Any feedback appreciated.
Thanks. Do we have a minute for questions? Maybe. I think we have a minute for questions, but definitely come find us after if you're interested in chatting. Loving legacy code bases, monoliths, and migrations.
Yeah, I mean, I would encourage to try the code. I mean, in this repository, you have the entire code I was demoing right now. You have the Envoy setups, you have everything set up. There's a deploy scripts there. You can run the scripts that would set up everything for you and you start experimenting on your laptop. Thank you.